So in the previous lecture, we started a discussion with what vectors are. Then we saw different perspectives of what vectors are from a computer science view, from a physicist, and from a mathematician's perspective. So we saw all of these three perspectives, and then we also discussed some of the things that can be done with vectors. Okay. So now if you just see these vectors, so from a computer science perspective, what they are just bunch of numbers, array of numbers. So if I have array of numbers like this, 2 3 4 2, this will be called as a vector. Okay, now you also have a notion of physics how they view vectors, and you also have a notion of how mathematicians look at vectors. But for now we'll restrict our discussion on these numbers. So this is the number. So when I speak about vector, so usually in the books it's usually written it as bold letters. They write it as bold letters, or they'll write, let's suppose, v, and they'll put an arrow on top. Okay, so v is equal to, let's suppose, 1 2 3. This is a vector, normal vector. Okay, if we have these vectors, so now based on how we write it, there can be two types. Just for the sake of completion, I'll write those. So two types of the vectors are row vector and the column vector. Okay, row vector and column vector. So what is a row vector? So basically we just write numbers in the row. 1 2 3 4. So this is a row vector because it's just one row of numbers. So column vector is a vector like this. It contains one column. So 1 2 3 4, something like this. Okay, so when you make a vector, as when we have arrangement of the elements horizontally, we call it a row vector, and when we have arrangement in a vertical direction, we call it a column vector. By default, whenever I say vector, this picture should pop into your mind. So by default, I'll talk about a column vector. So if I say vector, let's suppose I have vector v1 which has numbers 1 2 3 4. So the picture that should be formed in your mind is this: v1 is equal 1 2 3 and 4. By default we'll talk about column vectors. Okay, now we studied about what vectors are. Okay, what are the characteristics and these things. Now we'll see the key operations. Some operations we'll see. Key operations on these vectors. Do not lose the bigger picture. So vector is nothing but a representation. It's nothing but a representation. Everything that we'll see more or less will be a representation. Okay, we saw what is the position. Position was a point. That's a representation. Then we saw some quantities and we wrote them by numbers. Okay, and this is just a representation of something. Okay, now we'll have to perform something on that. If we have representation, we have to manipulate the representation in somehow to get some other representation. Okay, so what I mean, so here is, let's suppose this is a vector. It conveys some information to me. If this can, let's suppose I'll write something. Okay, to give an example, to give an analogy. So I'll say cat sat on the mat. Okay, if you see this sentence, it conveys a meaning. If I just jumble these words here and there, okay, I'll probably say mat sat on the cat. Just same words are being used, but numbers are probably, these words are shuffled here and there. Okay, let's suppose here you can see this mat might be a little mat on the floor, and cat sat on the mat. So here probably mat is a noun. Mat is some person who accidentally sat on the cat. Okay, so these two sentences are perfectly legal. Both of these sentences are legal, but both of them convey different meanings. So you saw the how arrangements differ. So if we have the same numbers arranged in different format, so probably they'll convey something different. So these are our words. Okay, this cat sat on the mat, they are words, but for a computer they're just numbers. Okay, let's suppose if we have numbers like this 1 2 3 4, so this is a vector. It represents something. Okay, so usually I say beauty lies in the eyes of beholder. Why do I say that? Because whatever is being in front of you, it depends how you perceive it. You see a picture, probably you will, whatever information that you have in your brains, you will extract information accordingly. So if you see this 1 2 3 4, so humans will extract some information from this. So if you have 2 3 4 1, it will be somewhat different vector. So they are entirely different vectors. Probably the composition is similar. Okay, by composition I mean the building blocks that made this vector, they are numbers and they probably are same, but when you put them in some order they make it different. Okay, that's what by operations I mean. So if I can do something to this vector so that I land at this representation, okay, this is what I mean by manipulation, what I mean by operations. So by operation I mean, okay, these vectors, now you should think them, something is physical, some physical thing is there, and then I have to have a mathematical construct for that. Okay, for a picture, let's suppose I told you yesterday also, if I have a picture like this, okay, so this is my picture and it's 28 cross 28. By that I mean 28 pixels here and 28 pixels here. So in total I have 784 pixels that represent this picture. Okay, so I'll have a vector of size 784. So I'll have a vector of size 784 cross 1. Okay, but I'll have these numbers. Okay, and let's suppose these numbers, I restrict myself to binary. Okay, it has just 0 and 1s, 0 and 1s. So 0 1 0 1 till 784 0. Oh, this is one picture. And even if I have some other vector, that will be some other picture. So what I mean by that is, if let's suppose I perform something on this, I do something with this vector, so that it is transformed to some other vector. It is transformed to some other vector. So that means it will be a different image. Okay, so if I made this 0 1 0 like this, I made it 1 1 0 something like this. So I transformed the vector somehow. And if this is vector of image, so this image will be one image and this will be other image. So now we are going to study what are the operations allowed. So I told you in mathematics we'll create a world first. We'll create a world and we'll have basic elements in the world. And after that, to complete that world, what we'll do is we'll have operations that can be performed in that world. Okay, so in the functions also we did that. We said, so if we have a problem template like this, and mathematics will generalize it like this. So similarly in our linear algebra, what I'm saying is the basic element is here is a vector. So now we'll see operations on vector. So right now I am just on the surface level. Once you understand this, then we'll go to the mathematician's view of what linear algebra stands for and what basically these vector spaces are and what vectors are. So now we'll see the operations. So I've written operations, key operations on vector. So what can be done? So the first operation that's very much used in everywhere, okay, that's transpose. So transpose of vector. So what is the transpose? Let's suppose if you have a vector like this, v, that is equal to v1 comma v2 comma v3. These are the elements. Okay, these can be anything. They can be numbers, they can be some other thing, whatever you want to call them. Okay, this is a vector. If I say v transpose written like this, or it's also written like v dash, most of the times you will write it like this. So this is just transpose it. Okay, so this here is a row vector. Okay, this here will become column vector. So by default I said I should write the vectors like this. So it's better to write it a column vector. So v is v1 v2 and v3. So v transpose or v dash will be v1 v2 v3. Okay, so I'll just make these rows into the columns into the rows. So that's the transpose. So if you have a row vector, it will become column, and if you have a column vector, it will become the row vector once you transpose it. Let's suppose we have a vector 1 2 3. So if I apply transpose on this, so it will become 1 2 3, something like this. Okay, this is, let's suppose, v, and this will be v transpose. Similarly, if I have a vector v is equal 2 3 4, okay, if I say v transpose, so that will be 2 3 4 like this. So this is one operation that can be done. Now we have a world, in that world we have vectors. So what we can do with vectors, the first thing that we saw is transpose. Okay, what does this transpose signify? Okay, so what it's some transformation. It does something. Okay, if I tell you what it does, let's suppose I'll show you what it does. Okay, so we'll take example of let's say a point, because we live in a 2D world for now. Okay, this is my point. Okay, so if I have this vector, so this is my vector. If I have a vector 2 3, so 2 3 basically means along the x-axis walk 2 distance. So this is this point 1 and 2. Along the y-axis walk 3 units. So this is 1 2 and 3 units. So I landed here. So this is my vector. Let's call this vector v. Okay, we call this vector v. So what is v transpose? Okay, so what's v transpose? Probably v transpose will be 3 comma 2. Okay, 3 2. So basically what it does is, if you see in the vector space, it basically transforms it. So here if you see this vector was 2 cross 1, here it is 1 cross 2. Okay, so what it does is, so this is no longer living in this 2 dimension now, this is living in some other dimension. Okay, you will probably understand it once more once we go to linear transformation. There we will show here, this basically is taking it out and it takes it to some other vector space, so to some other system. Okay, I won't use right now the pure mathematical terms, but I just want you to understand. Right now, here I had these 2-dimensional axes, and I said, okay, any vector like this can be represented in this 2D. So if I apply transpose, so what I said is, probably there will be some other system, there will be some other coordinate system. Maybe that coordinate system is made like this. So it took this vector and transferred this vector into this coordinate system. Okay, so transpose does this. So this is just a geometric interpretation of this. So once we go on these visualizations, there you will clearly understand these. Okay, then the other thing is, we can do what's called as element wise addition. Element wise addition. If we have two vectors, if we have vectors v1 which is like this, 2 3 4, and we have v2 which is like this, 4 5 6. So what I mean by element wise addition is, so v1 plus v2, this will be 2 plus 4 is 6, 3 plus 5 is 8, 4 plus 6 is 10. This will be nth vector. Okay, this is in terms of its numbers. So if we have numbers of a vector given to us, and then we can add it together. But let's say we'll restrict ourselves into 2 dimension. So what we can do is how can we get the numbers? Okay, so now we are learning about addition of vectors. Addition of vectors. So what I said is the first thing is I showed you directly mathematical way, if you have vector and just add them element wise. So now let's suppose we are in 2D. Okay, this is a vector and this is our origin 0, 0. If we have a vector like this, say let's suppose this vector is 2, 3, something like that, 3, 2, 3, 2. This is one vector, and maybe some other vector like this. Okay, so this vector, let's call it 2, 3. Okay, now we want to add these vectors together. Okay, so by addition, what I said is this addition is element wise addition. So what we should basically get, the answer that we should get is 2 plus 3, 3 plus 2. This should be our new vector. So this should be the vector, that is 6, 5, 5. This is the vector that we should get. Now how to get at this vector? Okay, how to basically get these vectors after the addition. So what we do is we have different methods at this. So the first method is called as tip to tail method. Tip to tail method. So in this, if I have a vector, I had vector this, and I had some other vector like this. So what I basically do is I'll shift this vector, the vector over here. I'll shift its tail on the tip of this vector. So basically this vector will look something like this. Okay, then I'll draw a vector from here to here. So this vector is the resultant vector. Okay, this is called as resultant. So why is it called resultant? Because it was a result of two vectors. And why is it called resultant? So what do I mean by addition? So I meant by addition, let's suppose right now if I take addition of these vectors, so here I'll shift it. So this vector will be shifted somewhere over here. Okay, so this is the shift of this vector. Okay, then if I map this to this, so you see this number will be 5, 5. Okay, this is that vector that we saw, what I call as element wise addition. You see the geometric interpretation at the same time. So what I am doing is I have two vectors. So now I am saying how to add these two vectors. The first question should be, what is the meaning of addition of the two vectors? The meaning of addition of two vectors is, let's suppose if we have a physical quantity. Okay, if we have a physical quantity, in that terms the meaning of addition is whatever effect this vector produced, and after that we had this vector, whatever effect these two vectors produced combined. So if we had these two vectors, they'll produce an effect. Okay, this vector, the resultant vector of these, will produce that effect independently. So it will have only one vector that will produce that effect. Okay, so let's suppose you did something, you had a vector and that produces some effect on physical quantity, and then you had another vector that also produced. By combination of these two vectors, you produce some effect. So the resultant vector basically produces that effect alone. So that's what is the meaning of resultant vector in terms of physical quantities. So so what in terms of image, what will be the meaning of this? Okay, sometimes what will happen is, so you'll have an image. So I said image basically is nothing but a vector. So image is a vector. So in our computer science terms, image will be just a vector because it's a bunch of pixels. Okay, and this will be a vector v1. And you might have seen filters. You might have seen filters on Instagram. Okay, when you have the image, and probably on Facebook also, you sometimes brighten the image. Okay, what you basically do is you perform some operation onto this. So let's suppose that operation is addition. So what will happen is it will manipulate all the values. Okay. So let's suppose if we are brightening the image, our image looks too dull, and if we are brightening the image, so let's suppose that brightening now has a number. So what we'll do, we'll say, let's suppose we'll plus this vector. We have a vector, okay, and we'll let's suppose this is v1, and I have flattened out version of this vector. So I'll add to all the pixels some number, some intensity number, which will brighten this image. So that's one of the examples how we use these vectors. Okay, it's a pretty basic example, but if you see how do we basically use that, there is a different, these are called as kernels what we use there, but here I am trying to justify that why are these operations required. So in the image, if you see, you do certain operations, sometimes you stretch the image also. So on a single image you can, let's suppose if you want to increase the size of the image, so what happens that time? This is also operation, because underneath what is it? It's a vector. Okay, it's nothing but a bunch of numbers. So what is computer doing with it so that it stretches? So when you change the color of an image, okay, let's suppose or maybe you are doing some other operation, maybe you give it some motion or something like that. All of these are basically operations on these vectors. Okay, so this is one method, tip to tail method. So you saw that basically what happens is, in mathematical terms, we are doing addition by taking each element. So 2 plus 4 is 6, 3 plus 5 is 8, 4 plus 6 is 10. So we are doing element wise addition. But if you see it geometrically, so geometrically a vector in 2D is like this. Okay, we can also make a vector in 3D. They are just lines of some sort. Okay, they are basically points. So these are points. this vector is a point, so this is a point. So when we add them, we reach here. So this is the resultant point of these things. Okay, this is one method of addition. So when you want to perform addition in physical senses, in geometrical senses, you will just take a vector and you will have its tip on the tail of other, and then you will compute the resultant. The other method is called as parallelogram. Parallelogram law. Basically, it's just similar to like that. Parallelogram. Okay, parallelogram method. So nothing special. So we'll basically get the same answer. These are just methods. Okay, again we'll have, let's suppose, some 2D coordinate system like this, and then if you have a vector, which is one vector is like this, and other vectors, let's suppose, like this. So if you want to know the resultant, what you can do is you can complete the parallelogram. By parallelogram I mean opposite sides should be parallel and equal in size. So this is the parallelogram, and then this diagonal. So this diagonal is the resultant. Basically, you are doing the same thing. Okay, this is just to show there are different methods of calculating the resultant, but more or less this is for your geometrical intuition. So this is what should be in your mind. Okay, this is how, when a vector is given, you should probably think about a line or a point. So this is a point, this is the other point. So if I combine these 2 points, I land at this point. Okay, if I combine these 2 points somehow, so I land at this point. In terms of image, so if I have one image, let's suppose I have one image, I have some other image. So what happens if I combine both of these images? What will be formed? Okay, let's suppose sometimes you might have seen, if I have some pixels like this, I'll make an image like this, some 9x9 pixel, and I have one pixel over here. Okay, and one pixel over here. Okay, then other image is like this. In that I have this one pixel. So if I combine these two things, if I add these two things, I'll get an image like this. So if I combine these two, so I'm saying this is, here we have ones and others are zeros. So they are darker here and rest is light. If I combine these, I'll be getting an image like this. So where I'll have something like this. So here, here and here. Okay, now you can see that. Let's suppose this was one pixel and this was other pixel. Here we had other pixel, and we just added two images. So we basically added these two vectors. So as we got this vector on the screen. Okay, this somehow looks like a 1, and this is how we can create different numbers also. So this is one significance of addition. So I gave you at least 2-3 perspectives how to think about these. Okay, from a CS perspective, this makes more sense. From a physics perspective, this also makes sense, because it's how you should geometrically see these vectors. Okay, and then the thing that you should see is when you add these vectors. Okay, when you add these vectors, so the size of these vectors should be similar. Size of vectors should be same. So when you add these vectors, size should be similar. Otherwise, you will have to do what's called as padding. If I have a vector, let's suppose, which is 1, 2, and I have another vector which is 1, 2, 3, and 4. So I want to add these two vectors. So now you can see this. I can add this 1 to 1. So if you want to now add in at any cost, so what you can do is you can pad this vector. You can say 1, 2, 0, 0. So you can, this is called as zero padding. Okay, you will pad these vectors as 0 and then probably add it. Okay, all these things makes more sense to computer science. Okay, rather than in physics, because probably mathematician will say these two vectors belong to different vector spaces. We cannot add them. Okay, they are from different vector spaces. But once you are in computer science, you have to see the application part of it. And sometimes you want to add. Then what you do is you do padding. This is called as zero padding, because you append zeros and to make the size similar. Okay, this is one of the operations that we said. The operation is that we can add two vectors. So the properties. Now we'll see the properties of these things, because I'll use these things to get you into the vector space, into the mathematical linear algebra. So here at least you should have this strong intuition. So now you saw these, we can add these two vectors. So what are the properties that these things hold? Okay, there will be some properties. So till now, if any questions, you can ask them. Any questions? So now what you saw is you saw a basic element is vector. So then there are operations possible on that. So the first operation that we studied was addition. We studied addition for these vectors. Now this addition has some properties. Okay, what are these properties? Let's say the first property is commutativity. Commutativity property. Okay, what is the meaning of commutative? So commutative means, let's suppose if I perform an operation, I have this vector v1, I have this vector v2. So what is this? A bunch of numbers for us so far. So what I'm saying is, if I can perform v1 plus v2, and I'll perform v2 plus v1. So if they give me the same answer, okay, then I call that operation as commutative operation. Operation commutative means if I reverse the order. Okay, once, let's suppose if I do v1 plus v2, if it came to be equal to v2 plus v1, so this is called as commutative. So you saw addition of vectors is commutative. Okay, why? You can also prove these properties because addition itself is commutative. So let's say if you see division, is division commutative? So if you do 1 divided by 2 and 2 divided by 1, this is not equal. Okay, division property is not commutative. So I'm just saying for the simple numbers, but for the vectors, the addition property here is commutative, if you see that. Okay, so the order in which you are adding these vectors does not affect the resultant vector. Okay, the order doesn't matter here. So we call this as commutative property. And the second property is associativity. Associative property. Okay, you might be thinking, why is it teaching us this? Because this is what will land you to the vector space. Okay, once we define the vector space, basically their element will be probably what's called as a field. So we'll have a field as element. Then we'll be having two operations there. We'll be having one addition operation and one other operation. We call that multiplication. But the addition is generic operation now, and then that multiplication will be again generic operation. Okay, associative property. Let me just finish it, then I'll take questions. So associative property is if you now have three vectors. So you have v, u, and let's suppose w. You have these three vectors. What you can do is, if you performed u and v first, and you added these two vectors first, and for that then you added this. If this was equivalent to if you performed u plus w first, and then you performed v onto this. So if this is equal, so what I mean by this is, you had to add three vectors. Now you have to just certain order to add these vectors. So if somehow that doesn't matter, so we can associate any two vectors. You associated u and v here, and here you associated u and w first. So and still the answer came to be similar. So this is called as associativity. So here I'll pause for a second. I'll take your questions. Yes. Okay, so the first property I said is commutativity, and second property is associativity. Then we have a property which is called as additive identity. Additive identity. So we should have an element which we call as identity element. So what is the meaning of identity? So if I have a vector v, if I added that identity element, let's call the identity element 0. So this should give me back v. Let's suppose for multiplication, what's the identity element? That's 1, because if I have 2 multiplied by 1, it is 1. So for addition, this 0 vector of zeros is the identity element. So identity should exist there. So if we have such property, if we have commutative property, if we have associative property, additive identity, and then we have one more property of this addition. Okay, all of these properties, once we go to the vector spaces, it will become clear. Okay, once we define the operation and the field, basically field will have elements, and these elements will be operated on some operations, and then we'll say, are they following these properties? If they are following these properties, then only it will qualify as a vector space. So here you see additive identity should be there. Then we should have an inverse. So what's the meaning of inverse? So inverse is, if we have element v, so this operation is some other v we should have, which will give me this identity element. So if I have a vector, and then I should have some other vector. Once I perform this operation of addition, it should give me the identity element. So here I am not calling it 0, I am calling it identity element. Okay, so let's say in case of multiplication, it will be 2 multiplied by 1 by 2. Okay, because this will give me identity element, because this 1 is my identity element. Here in terms of addition, 0 is my identity element. Okay, is it clear? So far what we have seen is addition here on real numbers. So addition on the vectors which have real values. So here all the elements of these vectors, they contain real values, 2, 2.4, 6.3, something like this. And then if we perform addition on these things, if we perform addition, we saw some properties it holds. So it holds this property of commutativity, associativity property, and then we have, it also have additive identity, that is, this should exist if we have an element such that if we add it to any vector. So if you take any vector from this, and if you add the vector of zeros, it should give me this vectors back. Okay, and inverse basically means if I have a vector v, and then I should have a vector, some other vector also, which once I add that, it should give me identity element. So these are the properties that apply for this addition of the vectors. So because now what I told you, I said that this will become generic once we go to vector spaces. So there we'll have, for now we have this real numbers, vector of real numbers, and then we define an operation addition. Okay, so far we have done this. So there we'll replace this real number with some what's called as field, and we'll have the same symbol addition, but it will be defined in some other way. Operation will be defined, and then we'll see if it follows certain properties. If it follows those properties, probably all these properties, then we'll call it, this is a field, and then we'll have one more operation. Okay, and this field will be having basically element. This field will be some sort of set. Okay, it'll be a bunch of let's suppose here real numbers. If we are in R2, that means I have numbers like this, 1, 2, comma 3, 4, something like this. Okay, this will be an uncountably infinite set of numbers if I am working in R2. Then I define an operation on this, addition operation. I told you this addition, the definition is that I will have the addition element wise. So I'll perform this addition with this addition with this, so as to get the resultant vectors. So what I said is, so with this operation and this, let's suppose this is a field now. With this operation and this field, okay, it follows certain properties. This addition follows 4 properties at least that we saw: commutativity, associative property, and then we saw that additive identity is there, and there is an inverse also. Okay, and then this a real field, or this field, this R2 field, it will have a generic field after that. This addition operation will be we will have some other operation there, but it will be still symbolized with this plus, because we will out of symbols. We have to have some symbol, and then we'll have this multiplication. These will be 2 operations, and this will be our field. This will be basically our elements of that vector space on which we'll operate, and then if they follow certain properties, we'll call that as a vector space. So far is it clear? So we saw addition of vectors. Again, not going into more detail, so I'm saying we just think vectors as bunch of numbers. We have these numbers and we want to add them together. So what we do is we do element wise addition, and then we saw some properties of the addition. I hope that this was clear. So now the other operation is that it's operation called as scalar multiplication. So whatever I am teaching right now, so the whole motto of this is to at least give you some geometrical interpretation and show you how to visualize these things. So I told you how to visualize addition of vectors in terms of these vectors, in terms of these lines where we had these vector lines, and in terms of these points also, and in terms of if we have some image. Let's suppose if we have this scalar multiplication. So scalar multiplication, by that I mean if we have a vector v, let's call that vector, we have vector v1, v2 and v3. So scalar, if I have a scalar, by scalar a is basically just a number. Okay, it's not a vector, it is just a number now. So if I write a multiplied by this vector v, okay, let's call this vector v like this. So this basically will multiply each of this element, a multiplied by v1, a v2, a v3. Taking a physical example, if we have 2, 3, 4, okay, if I multiply it by 2, so it will become 4, 6, 8. So this is the scalar multiplication. So if we see it like this, if we see it on that 2D coordinate system that we have been seen. So this is my 2D coordinate system. So this is my origin. If I have vector like this, so let's suppose this vector over here, this represents say 2, 3. Let's suppose 2, 3. Okay, now if I multiply it with a scalar, if I multiply it with let's suppose 4. So what it basically will do, it will stretch the vector. So here it will, what it will do is it will stretch or squish the vector. So what I mean by stretching or squishing, so either if it's a positive number, so what will happen there is I'll just probably double or triple it. Here I'll make it 4 times. This vector will become 4 times. So if this vector is represented this on the screen, so what will happen is this will be stretched. Or if I have, let's suppose, a number which is let's say 0, so it will get squished. Okay, if a number is, let's suppose, between 0 and 1, so what will happen by this 0 and 1, it will squish the vector. So in that, if I multiply it by 1 by half, it will make the vector 1 by half. So it will make vector like this. So if I, let's suppose, double the vector, it will be 4, 6. So 4, 6, let's suppose, is here. So this will be the vector. So if I multiply it with a number which is greater than 1, okay, it will increase the size of the vector. If you multiply it by a number which is between 0 to 1, it will squish the vectors. Okay, so if now you multiply it by the negative, so it will flip the vector. So it will, what it does is it will stretch, squish, or it will flip. Okay, it will flip the vector. So let's suppose if I multiply it by -1, so -1 basically will multiply it like this. So it will be -2, -3. Okay, -2, -3 is this quadrant. This is my first quadrant, second, third, and fourth. So this is what scalar multiplication does. If you multiply a vector by a scalar, so it can either stretch the vector, it can squish the vector, or it can flip the vector. And in the within the flip, it can again stretch it, it can again squish it. Okay, it can make it larger, make it smaller, or make it 0 even, because 0 also is a scalar. Okay, then it will make it as the origin. So this is how geometrically you should look at this. So once you see a thing multiplying a vector, you should think, okay, it will either stretch it, either what will happen is it will either squish the vector, it will make it smaller, or maybe it will flip the vector. Okay, that's what this by multiplication by a scalar can do. Okay, and after that, so if you see it in physical senses, what it can do. Let's suppose now this image, it has a lot of points in here. I'm just taking the example of image. So these vectors are all points. Okay. Let's suppose now we have a colored image. We have a colored image. So each of the element now will be, let's suppose, 0 to 255. So it will be, each pixel will be represented by 3 numbers: red, green and blue. Okay, and each of these will have values from 0 to 255. 0 to 255. Okay, because these are called as primary colors. So primary colors, we only need these 3 colors to make any color in the world. Okay, we can have the combination of these colors to make any possible color in the world. So we have these 3 channels now. We have red, we have green, we have blue. Okay, each pixel will have these 3 values, and each value here will be ranging from 0 to 255. Let's suppose if we talk about this pixel, so this pixel can be 200 of red, 400 of this green, and let's not 400, sorry, so 242 of this, and then 15 of this. So this will be a color. Okay, there are online websites where you can just open these images, and if you click on a pixel, it will show you this. It will show you how much green is there, how much red is there, how much green is there, and how much blue is there. Okay, so here what I'm saying is, so these, each pixel is somewhat represented by 3 numbers. So now if you are scalar multiplying that pixel, okay, if you are multiplying that with, let's suppose, 2, so now you can tell me, oh, 2 will make it larger. So here if you multiply it by 2, so then it will become 400. So this will become probably this will become 484. This will become 30. But this is not the range. So what we can do is, we basically what is called as wrap around. We wrap around in this case, because the acceptable value is only between 0 to 255. So what we can do is, if you have 2 multiplied by 200, okay, you wrap it around, you probably will take modulus with 255. What is the modulus operation does? I think in Python course we have done that. So this will get multiplied in certain ways. So right now what I'm saying is, you can change the values of each of these pixels. So today what you can do is, you can just try to go on some website and read the pixel values, and then what you can do is multiply each pixel value by let's suppose a number 1.5 or something. Then see what will happen to the image. That image will be somehow changed. Probably the color of the image will get changed. Okay, if you multiply each pixel by this scalar value. Okay, each pixel will have 3 numbers. So we have 3 vectors of each pixel, and then you have to multiply each of these pixels by that number. Let's call that a scalar. So now we again saw 2-3 perspectives. We saw that mathematically, if you have this vector v1, v2, v3, multiplication by a is directly this. So you just take that scalar and multiply it with each of the elements. So geometrically what it shows is that it basically either stretches, it squishes or flips the vector. Okay, in flipping also it will stretch or squish the vector. So in terms of image, I just took the example of image, and it can be any data per se. Okay, what it does is, you perform these operations, and these numbers will be then read accordingly. Whatever change you made to the number, so it will be read accordingly. So if let's suppose you have, because in computer science everything is number, so everything is an embedding. If you have this word cat, so cat basically will be represented by embedding, by some numbers. Okay, so if you do something with these numbers, if you do some let's suppose you multiply this with a, it will become some other thing. Okay, and this cat will be turned into some other thing. So there is a beautiful technique called as word to vec. So where we change this words to vectors. Okay, and that technique is so beautiful. Let's suppose if you have a woman, I'll just take a digression. We have woman, then we have man, we have king, and we have queen. So what you can do is, if you take this king, okay, and if you let's suppose this king plus queen, and this will be equivalent to woman minus man. What I mean by this is woman plus man, sorry. So what I mean by this is a vector. King will be a vector, a queen will be a vector, a woman will be a vector, a man will be a vector. If I add these 2 vectors, so they will give some resultant vector. Let's call that r, and woman plus man will give me some result. Let's call that r dash. So you will see this r and r dash will be almost equal. So this shows you power of these numbers. Okay, so in the similar fashion, so what I'm saying basically is, if you have these vectors, and then you will perform certain operation on these vectors. So here this is a classical example of word to vec. Okay, and then city with the capital. If you have a city, let's suppose if you have country is, let's suppose, India, and its capital is, let's suppose, Delhi. And if we can talk about some other Pakistan, let's suppose its capital is, I don't know, let's say Islamabad. Okay, so here if you see these 2 vectors, so if you, let's suppose, add or subtract these 2 vectors, if you take India plus Delhi, okay, and if you take Pakistan plus Islamabad, so both of these, the resultant vectors will be almost equivalent. So that's the power of this word to vec. Okay, and similarly here I am saying you that everything can be considered vector. Now we are learning multiplication by a scalar. Okay, it will scale a thing, and negative, what will be it will do, the geometric interpretation is this, it will scale. So basically all of these operations are called as scaling operations. That's why it's called a scalar. Scaling basically means you can stretch, squish, or flip it. Okay, and then now what you can do is you can also see certain properties. So it will also hold certain properties. So what are the properties? So it will be distributive. So by distributive I mean if you have this vector distributive or addition. So if you have the scalar, so you can write it CV plus CW. Okay, so this is called as distributive property, distributive or addition. Okay, then it will be associative also. If you have CD and V, so if you perform this first, this will be equal to, if you perform it like this. Okay, I don't now need to explain the properties because I hope that you will understand it. So here you can also have multiplication. So you can have this additive element. So if you have this, let's suppose scalar 1, so you multiply it, you'll again get this V back vector. And then you can have basically a 0 vector. So what it basically will give you, it will squish the whole thing. So you have 0 multiplied V, that will give you 0. Okay, it will basically give you nothing. So if you multiply it with a 0 element. Okay, and then we'll basically move on to some other operations. So the applications are enormous. If you see in applications, you can use it in physics, you can use it in computer graphics. So one basic thing is in computer graphics, you can use it to resize things. Okay, as I showed you, you have to resize things, so you can use to resize the things. So if you have a size given to you, and then you want to resize the things, you basically are performing scaling operations. Let's suppose that the scale of these elements. So each pixel, let's suppose, is of some value. Now what you want to do is you want to stretch the whole pixel. You want to basically increase the pixel value. So what you can do is with each pixel you will make them 2 pixels. Okay, what you can do is you can copy these pixels and then you can resize the element. So that will again be done by using this. You can just basically have these operations of scalar multiplication. If you just multiply these and just resize the things. Okay, and once you get into graphics and visualization, there these operations will matter a lot. Is it clear? So far what we have seen is we at least saw this addition. We saw this scalar multiplication or multiplication by a scalar. Now what we'll see is we'll see most of the important concept, most of the important and beautiful concept that is used everywhere. This is called as dot product. Okay, so where this dot product came from? So basically, now if you saw that we saw addition, we saw multiplication by a scalar, then can we somehow multiply two vectors? Can we somehow see multiplication of vectors? Multiplication of vectors. So there what we saw is there are two types of multiplication of vectors. One is called as dot product and one is called as cross product. So if you multiply vectors, so if you have vector v1 and if you have vector v2, okay. So now I'm asking a question: is the multiplication of vectors applicable? Yes, it is, but not in the similar term. So what we have there is you can perform a dot product and you can perform a cross product. So more or less we will be concerned with the dot product. In computer science, we will be more or less concerned with dot product and maybe sometimes also with cross product. But here we'll take this dot product in detail. So because this dot product is such a beautiful concept and it is used everywhere and it has a lot of physical significances that we use it for. In computer science, we use it for a lot of tasks. Okay. So what is this dot product? So now let's define it first mathematically, then we'll go into explain geometrically. So if we have a vector, let's call this vector capital A and the elements are A1, something like this, A1, A2 and A3, these are the elements. Okay, and then I have a vector B. Let's call this vector B, which is B1, B2 and B3. These are my two vectors. So what I mean by dot product is now, so by dot product I mean what you can do is you can multiply these things element wise. Okay, usually how we write dot product is like this: A dot B. Okay, this is my vector A and this is my vector B. So A dot B is known as dot product. So what you can do is you can do A1 multiplied by B1, then add it together. The question is, I'll come to the question. A2 B2 plus A3 B3. Okay, so what I'm saying is this is the definition of dot product. This is by definition. So what we're saying is, what you basically do is you multiply each of these elements, each of this basically they are called components of vectors. You multiply the component of each vector and then add them together. Okay, this is what is called as dot product. So here if you see, you will get a scalar as answer. So you'll just get one number. Okay, that is just a scalar. So that is the answer to your question. The question asked was, why is there a need of two ways of multiplication? Because sometimes if you multiply two vectors, so they give you output as a scalar, and sometimes if you have to multiply, they have to give it as a vector. Okay, and multiplication, I said, don't think it just as multiplication the way you have been taught. Multiplication 2 multiplied by 3 is 6. This is multiplication. So multiplication is an operation. Here we also named it as multiplication. But now if we have two vectors, if you perform an operation on that and that operation gave you a scalar quantity that just gave you one number. So that's why we call that a dot product. And if we have an operation, if we perform that operation onto these vectors and it gave us back the vectors, but still that multiplication is there, this multiplication is involved there, we call that as a cross product, because in cross product we'll again get a vector. And what are the physical significances? There are enormous physical significances. Dot product basically can be used, let's suppose, to see the similarity between things. That will come. I hope this answer clears the question. So if we take this dot product, so what I say is basically if we have vectors v1, this vector was 1, 2, 3, and we had some vector v2, and this vector was 3, 4, 8, something like this. Okay, so there has to be an operation, because these vectors I told you are physical things. They are physical things now. Let's suppose vector can be an image. Okay, vector can be some force. Force is a physical thing. Okay, so what if we have to find similarity in these things? Okay, what if we have to find similarity? The question asked was, did we saw these things in the nature and then we defined the operations? So what I'm justifying the answer. So I'm saying we had two vectors v1 and v2, and we have to somewhat see what is the similarity of these two vectors. Okay, so what we can do is we can perform the dot product. So how I define dot product is, I said dot product is defined like this. So this is my vector v1 and this is my vector v2. What you can do is you can just perform the multiplication like this: 1 multiplied by 3 plus 2 multiplied by 4 plus 3 multiplied by 8. Okay, so here what you will get a scalar number. Here you get a scalar. So somewhat what it can tell you, it can tell you how much similar they are. Okay, so this scalar value will tell you how much similar these vectors are. So let's suppose if this value is really high, so it can tell you these vectors are this much similar. Okay, if you have vector v1, v2 and v3, to make it more clear. So if you perform dot product of v1 and v2, if you perform dot product of v2 and v3, then you want to see, is v2 more similar to v1 and is it more similar to v3, because they're physical quantities. We're just taking the similarity of these things. Okay, there you can perform dot product. There you can perform a product like this and you can come up with a scalar value. So that's why you might have seen a dot b. If we have these two vectors, it's also defined as a b cos theta. Okay, a b cos theta. So there what will happen is, so if we have vector in like this, so I'll just explain it 2D. So this is my vector a, this is my vector b, let's suppose, and this is my theta. So if this, we have this a, b and cos of, let's suppose, 90. Because cos of 90 is 0, this will be orthogonal to each other. This will be somewhat like this. So you see that they are pretty much dissimilar. By similarity I mean how far apart they are from. So now with similarity there can be different notions of similarity. Similarity can be, are the images similar? Okay, probably are these forces similar? So what sort of thing? So here I am just saying one similarity. So if these vectors overlap on each other, let's suppose we have vectors like this. So this is one vector and this is other vector. It overlaps and theta here is equal to 0. Then you saw that this a dot b is directly multiplication, magnitude of a and multiplied by magnitude of b. You directly do it. Okay, and you see this, and then you will see, okay, whatsoever number is, that number will basically define the similarity. Here you saw that these are at the angle of 90 degree. So I just said you one thing. So one property is we want to define similarity. So if we want to define similarity, there we use the dot product. Okay, if many of you have seen, if you just going ahead, taking a digression and pausing the recording also here. Wait. So here what we saw is dot product basically. So we saw we have two products. One is called as cross product, one is called as dot product. But we will be concerning about dot product. So I said, so that one interpretation is you do multiplication element wise. So if we have vector a, if we have vector b, if the values are a1, a2, a3, and b1, b2, b3, b2, b3. So what you can do is a dot b can be written like this: summation of ai, bi, I equals from 1 to 3. For those who doesn't know, this summation is for the shorthand notation of this, if you have to add some things. So here it will be a1 b1 plus a2 b2 plus a3 b3. Okay, this is called as summation. Then we have one more. If we have something like this, a1 b1 multiplied by a2 b2 multiplied by a3 b3, in mathematics we write it like this: pi of. So this pi basically means product. Okay, pi of I goes from 1 to n ai bi. Okay, this has nothing to do with dot product, just a small notation detail. Okay, I told you mathematics is like poetry. You must know the vocabulary to understand poetry. So this is how I defined mathematically. This is the dot product. So if you see the geometrical interpretation, what I said that, so geometrical interpretation is that if you have these two vectors, I'm telling you this because I said it just a while before. So this is my vector A and this is my vector B. Okay, geometrically if you have to see, okay, this A dot B, so what is it geometrically equal to? This is geometrically equal to magnitude of A, so whatever this magnitude is, okay, plus magnitude of, not plus, multiply the magnitude of B, so this is what the magnitude of this is, and then there is the angle theta within them, cos theta. Okay, this is what it geometrically means. Okay, so I said one application is similarity. You can see the similarity. So here if you see, if I make this angle 0, so if I make this angle 0 is, then what vectors are? Basically vectors are parallel. So vectors are parallel if I say 0. If I say 90 degree, vectors are orthogonal. Orthogonal basically means when they are at the angle of 90 degrees. Okay, so you can see this. So this basically gives somewhat a different notion. So this is dot product geometrically, so it defines this. So if you have A, if you have B, so what is the magnitude of A? So we have seen this magnitude also. Okay, if we have this vector A1, A1, A2 basically, because it has just two dimensions, A1 and A2. So what is the magnitude? So magnitude basically means distance from the origin. So that is A1 square plus A2 square under root, because that is this distance D1. That is the distance d2. So d2 will be under root of b1 square plus b2 square. So that's this magnitude, and cos of theta, whatever angle they have made. Okay. So even if you know these things, now if you know this a1, a2, a3. So if you know a1, a2, let's suppose b1 and b2, these are two vectors. You can find the angle between them. Okay, because you know a dot b is equal magnitude of a, magnitude of b, cos theta. If you have to see what is the angle between them, what you can do is you can say a dot b, perform their dot product, divided by the magnitude of a, multiply the magnitude of b. So this is equal to cos theta, and theta is equal to cos inverse of a dot b divided by magnitude of a, magnitude of b. Okay, and you know how to compute this. You know how to compute a dot b. This is a1 b1 plus a2 b2. You know how to compute this. This is a1 square plus a2 square under root, and this is b1 square plus b2 square under root. And then you know if you apply cos inverse of that, you will get the theta, you will get angle between them. So this was how to compute angle, how to compute the angle between vectors. Okay, so if you know the components, if you know these values, if this is a vector, this is a vector, this is my vector a, and this is my vector b, so this is how we compute the angle, because the formulation is this a dot b. This is by definition, this is definition. So if you say me where does this come from, this is how I chose to define it. Okay, the definitions have no question. So this is how I define my dot product. So dot product I said is a dot b is equal to ab cos theta, and then I said this a dot b, because now I know the components, I can perform it like this. Okay, and then this value of a, value of b, because we have seen distances, distance from origin. So this is the formula of that, and then we can also compute the theta from that. So this is like sort of how you can compute theta, and from the theta you can see, are these vectors parallel, are these vectors perpendicular, so how will these vectors look in the space. Okay, that's one of the geometrical interpretation of these vectors. Basically I also gave you the example of these transformers. There we see how much contextual information is there. So I said the cat sat on the mat, so there I said, okay, so what word should be related to what word. So I said this cat, probably this is what sat on the mat, and on and let's suppose mat also have some correlation between them. Okay, and these things are captured by dot product. Is it clear? So what I'm saying, if a dot b is greater than 0, if a dot b is equal to 0, so what will happen is, if it is equal to 0, it means perpendicular or orthogonal. If a dot b, if you multiply these vectors and this came out to be greater than 0, that means the angle between them is acute, as less than 90. If you say a dot b is less than 0, so that means obtuse angle. Okay, so like this. So a dot b is 0, that means this and this, the vectors are somewhat like this. And then acute angle, if we have a dot b is greater than 0, that will be like this. Obtuse basically means which is greater than 90, angle will be something like this. Okay, this will give us negative values when you perform dot product, this will give us positive value, and this will give us equal to 0 value. That's how you should think. Once you know something about dot product, you know a lot about these vectors. Okay, if somebody tells you that dot product is 0, you can short say these vectors are perpendicular to each other. Okay, and if they say dot product is greater than 0, you can say the angle they form is acute. Okay, or if it is less than 0, angle they form is obtuse. So you also got the meaning. So how to compute the cos theta. If somebody tells you the components of these vectors, components can be like this, and then you can form the I'll make this formula more generic. So this over here dot product is, so to summarize this, so dot product To summarize this, so if we have A dot B, so how you define it? Summation of AI bi, I goes from 1 to n. So this can be an n-dimensional vector. We don't know. It can be, for n can be anything. Okay, and then we also said A dot B, this is equal to magnitude of A, magnitude of B, cos of theta. This theta is the angle between them. So I said this is the distance from the origin. So how do we compute this? This is summation of AI whole square. I goes from 1 to n, and this over here is under root of bi square. I goes from 1 to n. Okay, so this is for the generic if we have nd vector. Okay, and then we can also compute theta. So how to the theta that we computed was cos inverse of A dot B divided by magnitude of A, magnitude of B. Okay, so this is somewhat a dot product. So it can be used in different ways at different things. So it basically produces scalar. This gives us a scalar value. So this is a scalar value, and that value, probably one thing application that I said is it can describe similarity. Probably it can describe similarity. So is dot product clear? Is it clear?
I just one question.
Yes,
Do
yes.
these vectors have the same dimensions?
Yes, yes, yes. For in order to perform dot product, they should have same dimensions. Again, because otherwise you will have to do that padding, because here
I think
if component is missing.
I think I was reading about this for last 3 years about attentions and all, and luckily, surprising, I didn't know how to say this. A kind of joke I first time understood today that why do we take dot product and attention, and now I understand because we want to take the correlation, and it should be because for the yeah, and we get the correlation matrix as well in some cases,
Yes, yes, yes.
not in the attention but in other cases. But now I understand the fact that two same vectors cos would have angle 0, and cos 0 is the highest, that means 1, that's the
Yes.
highest correlation, so it will be like that. Yeah, thank you.
So
I am
that's the best compliment I can get, huh? And you owe me a gift. You said if I understand maths, I'll give you a gift. You better start packing, huh?
yeah, yeah.
So it's a good thing, but I need to cover projection. That was the plan. I need to cover projection. So I'll cover. Give me maybe 10 more minutes. I'll cover the projection, and then we'll be done with at least one part of basics. Then we'll move on to conic sections. Okay. Okay. Now we'll discuss about projection of vectors. Projection of vectors. Projection of one vector onto another. We can just say projection of vectors. So what I mean by projection is sometimes what you can do is you can project one vector onto other. Okay, this projection has uncountable, I'll say uncountable applications. Okay, and don't ask me how many applications, what are the applications, because we are not at the right point to discuss all the applications. So right now I'll say there are humongous number of applications that are there in the projection of vectors. So what is the meaning of projection? So let's suppose what I have is I will speak in 2D coordinate again, because this is very easy to make and very easy to visualize also. But all these also apply to higher dimensions. So let's suppose I have a vector like this. I have this vector. Okay, let's suppose I'll make this vector like this. I have a vector, let's call this vector B. Okay, then I have a vector, let's call this vector A. Do tell me if it's not visible, so I'll change the color. So this vector is A, let's say. So what I want to see is I want to see projection. Projection basically means some sort of shadow. What if I can put, I'll keep a torch in my hand and I can have, I'll directly at perpendicular angle, I'll throw light at this. I'll throw light at basically this A vector. So what will happen if you see, it will make a vector like this. The shadow will be like this. Okay, till here. So this shadow that I made with, maybe I'll make it with this color, some pinkish color. So here you see this will be the shadow form. So this over here is called as projection of A onto B. Okay, you also see the notation. This is called as projection of A onto B because this is how it was projected. That's why it's called projector. What it does basically is we have a projector like this and it basically throws light onto the wall, and then we are saying we projected it onto the wall. Okay, what we have here is we have vector A and we have vector B, and what I want to do is I want to project this vector A onto this B. I want to project this vector. I want to show that how will this look if I am restricted only to look into the realm of B. Let's suppose we are in some dimension which is 5D dimensional, and I want to see how my data will look in 2D. So I project my data from 5D to this 2D. Okay, that's one of the applications. This projection is used in dimensionality reduction. Again, I won't explain this. Because that's why I want to come. I want you to come back to these lectures, and then these things will make more sense to you. So let's suppose if I have a vector which has 5 components like this, 5, 4, 6, 8. Okay, but it's a lot of information. What I want to say is, I am saying, can I somehow represent this vector with less numbers? Let's suppose only 2 numbers, some 8.6 and 9.4, with in some other in some other plane. So this is in 4D, and this is let's suppose in 2D. Can I do this? But the comparison that I am doing is, it should have minimal loss. It should have minimal loss. So basically I want to do compression. So instead of represent something with 4 numbers, I only want to represent it with 2 numbers. But this compression, the loss that will happen should be minimal. Okay, this is called as dimensional reduction. I am reducing the dimensions from 4 to 2 dimensions. Okay, so what should I do is, I should project this 4D vector into 2D vector. I should project it somehow. Okay, that's what I'm saying. The projection is, if you have this vector A and you basically want to convey, you have 2 vectors A and B. Now you only want to retain the information of B, and you are saying, I want to retain information in B. I somehow want to see how will this A look if I projected this A vector onto this B vector. That's called as projection of the vectors. So I said this is represented like this, projection of A onto B, and we'll see the formulation, how to basically compute it. Okay, now let's derive it. Like, seriously, again, I don't know how to derive it. Right now, if you ask me to give me the formula, I don't remember the formula. So now I have to think a way, and again keep the eye on my thinking, how I will think. Okay, because now I basically want to do is, this is my one vector and this is my some other vector. Let's suppose this is some other vector. This is my vector B and this is my vector A. So I want to compute this projection. I want to compute this. I want to compute this portion. Now if you see this again is a vector. Okay, let's call this projection, let's suppose some D. Okay, this is my vector that I have to D, and D again is a vector. So now it has 2 things. It will have direction as well as magnitude. It will have magnitude and it will have direction. Direction I know. I can check this list. Why? The direction is along the B. Wherever B is directing towards, this D is also. So I am not worried about direction. I can find direction easily. Now I am worried about magnitude. How to find the magnitude of this? So what I can see is, let's suppose this angle is theta. If this is given to me, this can be theta or something else. So I want to see what is the projection. I basically want to compute projection of A onto this vector B. Basically this D I want to find. So I want to find its magnitude. So how to do that? Okay, let me do it like this. A dot B, this is a dot product. This is my A and this is my B. This is equal to A B cos theta. Everybody agrees on this? So because this is by definition. And now I am concerned with this D. So what a peculiar property I have found is this. So the property that I found is this D and this B vector. If you see this, somehow this B vector will be, or this D will be some lambda times of B. Okay, I'll have to find this lambda basically. I'll have to find how many times is this. So what I can do is, so this, if you see, this is a right angle triangle over here. This is a right angle triangle, and if you see this D, so this D is equal to A cos theta. Okay, in this right angle triangle, so we know that cos theta is equal base by hypotenuse. Base is equal to this D. Okay, and then we have this A. So I want to find this D. So D is equal to A cos theta. So here I can see this. So D is equal to magnitude of A cos theta. So here if you see this, so A cos theta is here. So can I replace with this with D? Yes, I can. So A dot B is equal to B times magnitude of B multiplied by D, and I want to find this D. So this D is equal to A dot B divided by magnitude of B. This is the magnitude I found. Okay, now what I am saying you, I am telling you that the direction basically is along this B, but this B is not a unit vector. I'll have to make unit vector B. So what is a unit vector? So unit vector is a vector which has the norm of 1, so whose magnitude is 1. So let's suppose I have a vector, call it 3, 4. So is a unit vector? No. So how to make it unit vector? So what I can do is, I can take these components and divide by its magnitude. So what is the magnitude of these vector? So 3 square plus 4 square under root. So this is 9, 16, this is 25, this is 5. Okay, so I can say 3 by 4 and 4 by 5. So 3 by 5, sorry, 3 by 5 and 4 by 5. This vector is a unit vector. Okay, this is a unit vector. Why? Because if I now take its magnitude, this will be unity. So if I say 3 by 5 whole square plus 4 by 5 whole square, so under root, this will be equal to 1. Okay, so A unit vector is a vector whose magnitude is 1, and we learned how to take magnitude. Magnitude means nothing, just take the distance from the origin. So distance to the origin is this. So if you compute this one, so if you have this vector now, a vector, which is a1 a2 a1 a2 an, let's suppose till an. So how to compute this, how to compute its unit vector? So it will be, take this whole a and divide each the element with the under root of I goes from 1 to n, this square. So this is my unit vector now. I just took an example of 3 comma 4. So a is 3 comma 4. So if I have to make a unit vector, so I'll take this vector 3 by 3 4, and then I'll divide it by under root of 3 square plus 4 square. 3 square is 9, 4 square 16, 16 plus 9 is 25, 25 root is 5. So this is 3 by 5, 4 by 5. So this vector over here is my unit vector now. So this a is a vector, its unit vector, which is written like this, a hat. So this is a unit vector. So now I need to find the unit vector of b. So okay, so magnitude is found. Now direction is, the direction of d is along the direction of b. Okay, so b is b divided by, take this norm of b. So this is called as, this is magnitude of b, take the magnitude and divide it with b. So the total vector that I want to find, this d vector, so this vector is equal to a dot b divided by b multiplied by b. So this is a vector b divided by b. So this will be equal to a dot b, b square dot b. So this is projection of a onto b. So projection of vector a onto b is dot product of a by b divided by magnitude square multiplied by vector b. So this is how you compute the projection, and you will get this vector, the vector that's over here, this vector. Magnitude is d, and magnitude basically is a dot b divided by norm of b. And then if you have direction also, so you just multiply it by unit vector of b. So that gave you the whole vector. The whole vector is like this. So you should know this formula, and you should know how to derive this formula. Okay, and if you ask me tomorrow, okay, what the formula, I won't probably know. I should be able to derive the formula. So what's the projection? So projection is, if you have high dimensional thing and you want to project it to lower dimension, you should use this formula that time, a dot b and then b square, and then there is projection is there needed. So just think it like geometrically. You have vector b like this, you have vector a like this, you are keeping a torch on the top, okay, and then this is making a shadow on here, and this vector over here, this vector till here is known as projection of a onto b. That's equal to dot product of a and b and divided by the magnitude of b square. This is called as L2 norm. We'll see what the L2 norm is, and then multiplied by b. Okay, so this sort of covers the basics of what I had to talk about vectors. And now from the next section onwards, what I'll do is I'll go to these lines and these conic sections, lines, different decision boundaries. But here I'll take one more session on that, and after that we'll code most of these things. We'll start coding from a point, from this 2D plane, Cartesian plane, 3D, and then we'll see distances, we'll see the cross product, we'll see dot product, and we'll see everything geometric. Now we'll see it on the screen. So I'll stop the recording here. If you have any questions, please feel free to ask.